Hi, this video extends the concept of exact differentials from 3 dimensions to 4 dimensions. If we have z as a function of x and y, we saw that an exact differential dz was expressed as p dx plus q dy, and it was only an exact differential if the derivative of p with respect to y was equal to the derivative of q with respect to x. So we now want to extend this to another function, but in 4 dimensions. We could have a new function w, and w is a function of x, y, and z. So instead of 2 independent variables, we now have 3 independent variables. So our differential is expressed in literally the exact same way. We would have dw equal to some p dx plus q dy, and we would now just introduce a third component of this, and that would be r dz. So for this to be an exact differential, the same criteria holds for 4 dimensions as well. So day p, day y is still equal to day q, day x. However, since we have this other component, we now need to introduce a few other constraints. So it works the same way using mixed partials as we had done before. So the derivative of p with respect now to z must equal to the derivative of r with respect to x. And that also means that the derivative of q with respect to z must equal to the derivative of r with respect to y. So these are the 3 constraints that we have to apply to prove that a function is an exact differential. So let's just look at a basic example to illustrate this point. We could have dw is equal to 3x squared yz, okay, that's a z, plus 6x dx plus x cubed z minus 8y dy, and lastly plus x cubed y plus 1 dz. So let's apply our constraints. So we would let p equal to this first term, we would let q equal to this second term, and we would let r equal to this third term. So the first constraint requires day p, day y, day q, day x, day p, day z, day r, day x, and so on like that. So we will evaluate these derivatives. So the first one is day p, day y. So finding the derivative with respect to y is quite straightforward. So that would be 3x squared z plus 6x, and of course that's just 0 since we're differentiating with respect to y. Then we need to find derivative of q with respect to x. So that would just be 3x squared z, and second term is with respect to y, so that's just 0 since it's treated as a constant. So we see that these two are equal, so our first constraint is checked. Then we now need to look at the second one, and the second one says we need to find the derivative of p with respect to z. So doing that, okay, we just have a z here. So that just disappears. So we're left with 3x squared y. Now we need to find the derivative of r with respect to x. When we do that, we get 3x squared y. And of course, 1 just disappears since it's a constant. And we see that these two are equal. So our second constraint is satisfied. Then the third one, we need the derivative of q with respect to z. So z is just to the power 1. So what we're left with is x cubed minus 8y, and 8y is treated as a constant, so it disappears. Then we also need derivative of r with respect to y. So this will just give us x cubed again. So we see that it's equal as well. So our third constraint is satisfied. So what this means is that dw is an exact differential.